Hello and welcome you guys to my new video in this video I will talk about the Taylor expansion of the logarithm function, the log function. And there is an easy way to do this derivation and there is a hard way to do the derivation. I will actually use the easy way, okay, because I'm lazy, and I will do the lazy way. And actually we don't want to calculate the Taylor expansion of the logarithm of x, but we want to calculate it of this function. Okay, you will shortly see why we choose this equation, or better this function. In order to do this, one just starts off with the integral equation that 1 minus x dx. Okay, remember from calculus, how can one find this? Actually, if we have the integral over 1 minus 1 over minus x, you remember, okay, we have some kind of fraction, and in the fraction we have a linear term of x. This is something like the logarithm, okay? But now let's look what it actually is. If I differentiate the logarithm, I get 1 over 1 minus x, okay, but then I have to use the chain rule and I get a minus in front of that. So let's just do a minus sign in here, okay, so that the equation is true. So we start off by using this equation. Actually, you could take this minus here, and I will do that. So this is where we start off, and now I will do another approximation, very important for us, that I will say, okay, listen, I won't use the whole integral, okay, I won't use the whole integral, but not the whole integral, but the whole domain. I will only look at values for x, the absolute value of x being smaller than 1, okay. Then you might ask, why is he doing something like this, telling us that the absolute value shall be smaller than 1, but you will see, if I can say that the absolute value of x is smaller than 1, then I can use the geometric series for this problem, and our function becomes a very interesting one. Okay, now what I've written, it starts from 0 to infinity, x to the n. This is the geometric series, and this is only valid for absolute values of smaller than 1. Now what I do is I look at this and see, wow, I have a sum and an integral. Actually, this is not that easily as I do, but I'm doing a lazy, slippery proof here. One can interchange them if some specific things are given, okay? And I won't tell you how to really prove this, that this is, you can actually do this, but we will do this, okay? We will change the integral sign and rewrite this like this, okay? But now, wow, this is a pretty easy integral, isn't it? So you learn in school, and this is pretty standard calculus. There is a way to write this n plus 1 x n plus 1. Actually, you could have a constant in here, but I'm letting out all the constants because actually you will see that the constant is equal to 0. Okay, the constant has to be 0. Why has it to be 0? Because if you plug in here the value of x equals 0, okay, what you will get is that this here will become 0, and left hand side you will have all zeros, and if you had a constant it would force the constant to be 0 too. So we don't need any constant. Now you look at this and see, wow, that's looking a little bit shitty. I want to change these indices, because you see this is starting from 0. Actually we will get 1 and here 1. So why not let's start this at 1, okay? And this is actually what we do. Now we have written this down, and it actually looks a little bit weird, but also interesting, doesn't it? Okay, actually if I write it down, let me write it down. It looks like this, okay? We plug in x over 1 plus x squared over 2 plus x cubed over 3 and so forth. So this is pretty cool, and actually you can now try to calculate some cool values. For example, if you would plug in minus, okay, you cannot do this, but actually one can show that you can even do this without having the absolute value of smaller than 1. Actually, one could plug in a value of -1, okay, and see that this series for -1 does really converge, and it has a value of logarithm of 2, okay. Now, this is not the only way to write this down, to pin down this equation. Sometimes people just introduce, instead of hitting -x, one can here introduce -x, so we rewrite x as -x, so we get here +x, and the sum will turn out to be -x over 1 plus -x is just x squared, minus x cubed 3, and so forth, okay. So it has alternating signs, and one can do that. Now I will show you what we can, for what we can use these values. I will just switch my table so you can, okay, to the left. So let's have a look at what we have until this point. We have found out that log of -x is equal to -x plus x squared 2 plus x cubed 3 plus blah blah blah, and we have the logarithm of 1 plus x. We showed we had a minus sign in front, so I will bring this back again here. We had a minus sign in front, and this means that we have x minus x squared plus x cubed, and so forth. So I will rewrite this: x minus x squared 2 plus x cubed 3 minus x 4 and plus minus and to infinity, okay. Now one could look at this equation and say, wow, this looks interesting. Somehow it looks interesting. Now why won't we do something cooler and just look at these? They look pretty similar. We have x, we have this and this. Why don't we just subtract both equations from each other, okay? I will, or better, we add them, okay? Add them or subtract them. Let me have a short quick view on that. If I subtract them, this will give me a problem, I think. Will it? I will subtract this from this equation. I will subtract this, okay. Sorry for thinking so long, but I had to think of a way so we don't end up having a lot more trash than before. So what will happen is we get minus minus. This means we are actually adding all these values, because this minus will cancel with this minus, and we are adding all these values. So we have 2x, okay, and this part are canceling each out. Then we have 2x cubed 3 plus this part and this part are again canceling out each other, and we get 2 times x 5 and so forth. So what we end up, actually you can rewrite this in a better way by using logarithm rules, okay. This is 1 plus x 1 minus x, and what we have here is 2 times x plus x cubed 3 plus x 5 x 7 over 7. So you can see this, and this is the way one can actually calculate with this formula any number for the logarithm. So if you want to have the logarithm of 7, then you can calculate actually with this formula by using only x values that are smaller than 1, and this is a very powerful formula. Just remember that, and actually this formula is strongly related to the Taylor expansion of the arcus tangent, and you will see that later on. But for this video, that's it. This concludes the lesson. We found out the Taylor expansion. Very important. This is again only true for smaller values of 1. Okay, that's it. Please subscribe for my videos if you want to see them all, because I'm adding them daily, some new videos. So if you want to stay tuned and see the latest videos of mine, just please subscribe. Okay, see you guys.